Okay, so what's the answer for titanium?
31.55%.
Yep. So this is what I was talking about. You might end up getting 5.5 instead of the 5.6. That could just come from entering it all in on your calculator at once versus doing the top and then writing down the bottom and then solving. So the last part is finding the mass percent of oxygen. So two approaches would be you could just solve for the mass percent of oxygen, or what's a simpler approach? Subtract from 100. All right, so solve that. So you should get 31.64%. You might be slightly over 100 or slightly under when you're doing the subtraction technique, or I guess not from the subtraction technique, that you would get 100%, but when you're adding them up if you solved for it. Everybody good with that? All right, so this is another simple mass percent, but in typical AP fashion, they're going to make it more challenging. So we'll read it, and then what's the challenging part? Tablet contains 0.025 milligrams of vitamin D. The entire tablet, however, has a mass of 0.115 grams. Calculate the mass percent of vitamin D in the tablet. So what's the trick? Grams and milligrams, right? So you have to know your metric conversions. Those are the 4 note cards I told you to make sure you made and memorized. So you use dimensional analysis. You either write it out or you do it in your head. And you first convert, then you solve part over whole. So the first step would be this conversion. So you need to know that there are 1,000 milligrams in 1 gram. So that's going to tell you to convert and move your decimal 3 to the left, or you just use your calculator to do that. And then you can do the part divided by the whole and then solve. So you should get 0.022%. And then 2 sig figs, because you have 2 sig figs in your vitamin D mass. Good? All right, the next problem, I don't think you would know how to do. Perhaps you would come up with some sort of approach. I certainly hope that you don't leave anything empty on any question, because you don't know how many points you get for doing simple tasks like writing out. Maybe you would have gotten a point for converting milligrams to grams on that one. Say you didn't know how to do anything else, but they gave you a point for that. So make sure that you write out anything really on a problem. It says a sample of potassium permanganate, KMNO4, is known to contain some impurities. So let's just pause right there. Occasionally I'm going to mention stuff because you're supposed to know it, and I know you don't, but the AP exam occasionally will ask a multiple choice question really simple, like, what color is the solution of a potassium permanganate? Do you know? But you should know because they expect you to do lab, which we will. We're going to see potassium permanganate at some point this year. So they expect you to know that you've used it in lab, so you should know the color of the solution. It's this really bright purple color. It's very pretty. So try to remember that P, permanganate, goes with P, purple. It's a purple permanganate color. And this sample is known to contain some impurities. So I like to draw pictures when I do any sort of solving, and I want to visualize what's happening. So I have a sample, and in it there's some impurities. So I literally would just draw something like that. So I'm visualizing that there's not just this one thing in there, there's other stuff in there also. It says then that it is found that K plus makes up 19.24% of the entire mass of the sample. All of the potassium comes from the potassium permanganate compound. Right, so in here is KMNO4. And then all of this K is 19.24%, but this KMNO4 isn't the whole sample, is it? Because 100% of the sample is made up of KMNO4 plus impurities. Do you get that? So if we were to just do a simple grams of K over grams of KMNO4, we would get a mass percent much higher than 19.24. The reason why we're going to get a smaller number is because we have additional grams here of an impurity. Following? So your approach to this now is to find the mass percent of KMNO4, which is basically that part over the whole mass. We don't have the whole mass. We don't have the mass of our entire sample, right? So we can't use that approach. But what you can do is recognize that you can use a ratio here. If you had grams of K plus and grams of KMNO4, that would give you the percent of K plus. But I can also relate this as a ratio to the percent of MK MnO4 as a ratio. So like the mass of this to the mass of this is equal to the percent of this to the percent of that. Are you following that? Because we would have said that anyway if we were doing it out of 100%, right? Because this approach would have been the percent of K over 100% of the sample. But it's not out of 100% because there's an impurity there, so we're going to figure out what its percent is just using the same exact ratio. Percent is always out of 100. It's just that this time it's not going to be out of 100. We're going to solve for it. So what you're going to do is make sure that you recognize this is an equal sign, so that means you cross multiply to solve for this piece, which is going to be x. All right, so I gave you the approach. Now you're going to plug in your numbers and solve. Okay. So here we have the potassium mass, and the mass of potassium permanganate just flipped because you can make a ratio any way you want. So the slides just flipped what I just said. So just look at your work the other way. Your 19.24% matches with your 39.10, and then you cross multiply, and you solve, and you should get 77.77%. Give me a thumb if you got that. No? What happened there?
I actually didn't add the potassium. Like the
Okay, so you just did permanganate. All right, so that's an easy fix. What happened over here? Okay, so just make sure that when you do this part, so these are your masses that you should have had, you're multiplying. So this should say 158.04 times 19.24. You don't have to change that out of a decimal into a decimal, I mean. You can leave it as percent because then your answer will be in percent. So it should look like this, and then you divide by 39.10, and then you divide by 39.10, and you solve. So that should make sense that they don't add up to give you 100, because what's the remaining percent? Thank you, David. The impurity, right? Okay. Moving on, we have empirical. So a molecular and empirical formula, very simply, a molecular is what I would say is the actual formula, but it may be an empirical formula also. And I'll show you an example of that. The empirical formula, I say, is the reduced form. All right. Looking at these examples, we have hydrogen peroxide is reduced to HO. C2H4 is reduced to CH2. Dextrose, reduced. So you just take your subscripts and reduce them if possible. If it's not possible, then it's already reduced. It's still the empirical. Go ahead and jot down the empirical formula for each of these. So first you have H2O reduced to H2O. Acetylene, CH, hydrazine, and H2. Good? All right. Before we start this problem, we're going to use the empirical formula rhyme. So those of you who had me, we practiced this rhyme. Oh, it's right there. Those of you who didn't have me probably just memorized the steps, but it's more fun to rhyme. So it goes percent to mass, mass to mole, divide by small, multiply till whole. Okay, so we're all going to say it together. Ready? Percent to mass, mass to mole, divide by small, multiply till whole. Oh, I don't think Tristan said it. I couldn't see. I'll move this way this time, and I'll watch to make sure you're saying it. I just want to make sure we say it twice, so I'm going to blame you. Ready? Percent to mass, mass to mole, divide by small, multiply till whole. Okay, now write it down. I wasn't recording our cheer. But this is the rhyme. All right, so now we're going to apply it to this. When we see percent to mass, that literally means take the percent sign and just turn it to G for grams. So the idea is that it's out of 100 grams. So if I said that there's 28.9% nitrogen, that just means it's going to be 28.9 grams. So you literally just write grams for all of these. And then you convert them all to moles using the molar mass. So I'm going to put them all down. Just jot them down. You don't have to look anything up. But I do pause for 1 second. I want to make sure that you recognize that you don't write H2. We're so used to writing diatomic molecules that it feels very awkward and weird to write it just as H or just as O. But you're supposed to do that for empirical. You will not have diatomics, so then your mass is just going to be 1.01. So go ahead and jot all this down, and then we'll discuss it. Okay, you should, when you do these, write your numbers out without significant figures. So when you're doing an empirical formula, your result is not numeric in the sense that you're not going to be writing out, like, these aren't your answers. You do get subscripts, so in a sense that is numeric, but you're really looking to give me a formula. And if you round for sig figs here, there's a good chance that you're not going to recognize the whole number. So remember, after you do this, you divide by small, all of them by small, and you're looking for a whole number in your calculator, right? But whole numbers are sort of vague because this is experimental data. So you might get something like 4.90. Is that whole? You have to make decisions at that point. Do you need to multiply or not? So common fractions are things that you need to multiply. Something like 0.16, 0.33, 0.5, 0.25. Those fractions would be certain kinds of common fractions that you would need to make sure you multiply till you get to whole. But something like 4.90, what are you going to do with that? I would round that to 5. But what if it's 4.85? That feels a little uncomfortable, right? To just say, it must be 5. In this exact example, I think it's hydrogen. I don't know which one it was. Yeah, hydrogen. Your calculator, if you round like this one did for sig figs, you're going to end up seeing a 4.85. If you don't round for sig figs and you just write them all out, you'll see a 4.90. That is more, that's more roundable, right, than a 4.85. So my suggestion to you when you're doing your empirical formula problems this weekend, don't round any of your answers. Write out as many digits as you can and then divide by small. So now if we divide by small here, you'll see, so you divide them all by small. That's what the next step says. So mass to mole, then divide by small. The smallest number was 1.03. When you divide them all, you get all these. But like I just said, if you take this and put this in your calculator, you're not going to get 5. You're going to have to realize that you have to round that. And it looks a little unroundable. So carry sig figs as much as possible. So after you get all of your whole numbers, you just put them as the subscripts. I do realize that some of the formulas you're not entirely sure, like which element should go first. But in a hydrocarbon, typically carbon goes first, followed by the hydrogen, and then any elements after it. If you mix up the order, you likely won't get any points off. But sometimes we do this for formula units for an ionic compound. I would expect you to know if I gave you, say, calcium chloride, that calcium goes before chlorine, right? Not the other way around. Everybody got this? Not yet. Wait a minute. Okay, so then our next step then would be to find molecular formula, which is the actual formula. It can end up being the same as the empirical. It just means that your number that you're multiplying by would be 1. So here's how you're going to do molecular. So you're going to take MM, which stands for molar mass, and divide it by the empirical formula mass, which is what you just found. You find those numbers by adding them up on the periodic table. You get some number, and you're going to multiply it by the subscripts in the empirical formula. So jot that down, and then we'll practice it. All right. The molar mass for caffeine is 194.2. Find the molecular. So when you look at this formula, the molar mass is always going to be given to you. The question has to give it to you because how else would you figure it out? You can figure, like this can be a calculated number, and you would have had to figure this out earlier on. But the molar mass has to somehow be given to you. So they'll either outright tell you, Or they're going to give you some other piece of information that makes you figure it out, like a graph of some sort. So I'm going to ask you guys to think. Last week I taught you about a specific instrument that gave you graph data that told you what molar mass was. Like the output was molar mass. Does anybody remember what the name of that instrument was? No, what was PES for? Everybody guesses that first because we spent most time on that. What was PES for? What did that give you? Electrons, right? Removal of electrons, energy to remove electrons. So PES data gave us electron data. Which instrument gave us mass data? Mass spectrometry. Spectrometry, yeah. Yep. Mm-hmm. So mass spec data looks like this, right? It's where you have like straight peaks. Do you remember that? And you get like fragmented data. But then this is how we used it for isotopes. This was like the 30, this was the 40, this was the 50, and then we could analyze it for isotope data, right? So that gives us mass data. It's possible that they could give you a problem like this and ask you, using mass spec data, find the molecular formula. So that means that you would go find your molar mass from a mass spec piece of information. I have not seen that myself on an exam, but that is typical of them, to tie in different graphical representations so that you figure it out. All right, so we don't have to do that. All we have to do is just divide the two numbers by each other. So you're going to add this up. That's what the empirical formula mass means. Add this up. 12 times 4, 48, plus 5, plus 28, plus 16. Type it in. You get a whole number, and then you multiply that number by each of these subscripts in your equation. So go ahead and try that. So after you divide, you get a coefficient of 2, or a multiplier of 2. So 2 times 4, 2 times 5, 2 times 2, 2 times 1, and this is your molecular formula for caffeine. Good?